Okay, now we'd like to talk about what's called the activity of the radioactive sample. So last time we talked about how stable our nucleus was. We saw that ones that don't have a decay mode are 100% stable. We saw ones that do have a decay mode, we could figure out stability based on half-life. Half-life, again, is the time it takes for half of the radioactive substance to decay. We saw that it was random and that we never know when a specific nucleus will decay. We saw what the graph looked like. And then we were talking about how do we figure out how much of a substance is actually present. So if you look at this little radioactive barrel and we see the particles shooting out in all directions, how do we know how many nuclei are inside of there? Well, hopefully it makes sense that the more particles we see shooting out is an indication that there are more nuclei present inside that barrel. We call activity the number of decays that happen per second to a sample. So if we had this barrel, the number of particles that shoot out in 1 second is called the activity. The more particles that shoot out, the more active it is. The fewer particles means it's less active. Now notice if we have a detector, that detector does not capture all of the particles. So we have to be very careful with our mathematics in terms of figuring out what percent of the particles we actually captured with our meter. Okay? So there's a lot going on today, so I want to make sure you have a good understanding of how this all works. So let's just start with the basics. Activity refers to the change in the number of atoms per second. So that tells us how many atoms have decayed per second. Activity. The best unit for activity would simply be decays per second. Now, unfortunately, just like with everything else, they're always trying to name units after different scientists. And the two most common units for activity are becquerels or Curie. Becquerels makes the most sense. 1 becquerel means 1 decay per second. Logical, simple. This is the standard we should be using when we measure activity. The problem is there's often so many decays that the numbers get really, really high. It would be nice if they just tacked on a metric prefix, and they can and they do, but the more common way of measuring it is based on Curies. Curies is a unit that dates back over 100 years now, and it refers to the activity of 1 gram of radium-226. Why that? Because that's what Madame Curie worked with, okay? When she was working with her radioactive substances, it was radium-226. It was one of the more common ones she worked with, and they wanted to compare the activity of their sample to the activity of her sample. Realize that her sample was incredibly radioactive, so hopefully you will never encounter a substance that has a radioactivity of 1 Curie. Okay, that's not good. So instead you'll see things like microcurie or nanocurie. But how much is a Curie? 1 Curie is the same as 37 billion becquerel. Okay, so if you want to convert from Curies to becquerel, which becquerels again are decays per second, there's your conversion. 1 Curie is 37 billion becquerel. 37 billion decays per second. So that sample she was working with was incredibly radioactive. Here is a former student of mine, former Delcy student, who worked at the University of Pennsylvania in their health physics area. She now is working for Yale. Great physicist. And in this example, she is trying to measure the activity of a sample that you'll see up against the wall. She was doing this to calibrate her Geiger counter, but I wanted to show you how this process works out. So she would need to know how far she is from the sample, how big her Geiger counter is, and also she would have to measure how many decays she's picking up per second. Okay, so you can see her changing the distance. And as she changes the distance, she picks up more and more of the decays that are happening. You can see she's using her Geiger counter to measure exactly how many particles she's detecting per second. And from that, we want to make sure we can figure out what is the activity of this sample. The activity, again, is a clue to how many nuclei are actually present at any given moment in time. Okay, so it says that Ashley's Geiger counter, that was the little circular thing that was picking up the radiation, has a radius of 5 centimeters. So the first thing you want to do is calculate the area of that Geiger counter. How much surface area does it have? Every piece of surface area is another place to pick up particles. Okay? The Geiger counter is placed 1.5 meters from the sample. So the Geiger counter might be right here. And again, you find that area. Now it gets a little tricky. You need to get the area of the giant sphere that that Geiger counter is part of. And the area of that giant sphere is 4 pi r squared. Now the r does not stand for the size of the Geiger counter, but for the size of that giant sphere. And then what you do is you set up a ratio. The area of the Geiger counter to the area of the sphere should be the same as the number detected to the number total. You want to find the number total. How many total particles shot out of this little barrel? You figure out how many were picked up by your Geiger counter, and you set up a ratio. What percent of that giant sphere that they could have shot out in was I actually picking up particles for? Okay, so try working this out. The Geiger counter, this little circle, radius of 5 centimeters. The area of the sphere, 1.5 meters. The Geiger counter picks up 1,500 decays per second. You're trying to figure out the total number of decays that happen per second. Okay, so again, activity is important because it lets us know how many nuclei were present in that sample. The more nuclei we had, the higher the activity we're going to measure. So oftentimes, if we're trying to use radioactivity to figure out how old the sample is, it's called radioactive dating. Very important technique in a lot of areas, such as when we're trying to do archaeology. Okay, we want to know how old something is. So what we need to do is we measure the activity now. We figure out what the activity should have been when that substance was created. And we see how many half-lives have passed. So we started out with 400 millicurie. After 1 half-life, we're at 200, 2 half-lives, 3 half-lives, 4 half-lives, and 5 half-lives. So you see how many half-lives went by, and then you just multiply by the half-life of your sample. So this is how we use activity and half-life together to date a radioactive sample. The final thing I'd like you to do today is also kind of tricky, so a lot of hard math today. And that is to figure out how much energy we can get from a radioactive sample. So when we sent different crafts to Mars, we start with the Pathfinder in 1997. It was the first mobile thing that we put on Mars that could move around and take a look at what Mars was like. Didn't get very far. We had the Spirit back in 2004, and that lasted for many, many, many years and brought back lots of important information about water in Mars's past. And you'll notice that both of these craft got their energy from solar panels. A simple way of keeping it going more than a couple hours, because after all, there's no gas stations or recharging stations on Mars. But at the same time, not the greatest source of power when you're on Mars and you're so much farther from the sun. And you're subject to having your solar panels covered with dust from Martian storms with no way of being able to clean them off. Okay? So when we sent a more advanced rover back in 2012 called Curiosity, you'll notice it didn't have solar panels. Scientists wanted to find a really good source of long-term power. So what they decided to do was use a radioactive isotope. They used plutonium. They used the isotope plutonium-238, and what they realized is that the plutonium-238 had a half-life of 90 years, meaning that in a 90-year time period, it would still have half of its fuel still remaining. Okay? Every time a nucleus decayed and shot a particle out, that particle was captured and that energy was turned into heat, which could then be turned into electricity. Okay? So they could then use this radioactive source as their energy source for a really long time. So I'd like you to see if you can figure out how much energy is created by the 4.8 kilogram sample of plutonium-238 during one half-life worth of time. All right, so it's kind of tricky. So take it slow. I'm not going to give you any other problems today other than the two I asked you to do already. That is the one with Ashley and activity, and this one with energy from the radioactive plutonium. So start by writing the decay equation for plutonium-238. So you got plutonium-238, 94-238 plutonium. It's alpha decay, and figure out what the reaction is going to look like. Hopefully you get something like this. Balance the charges at the bottom, balance the nucleons at the top. Next, what you want to do, and I'm not going to do this with you, you're going to do this on your own, get the mass of this, then get the combined mass of these two. They should not be the same. We know that some of the mass is going to disappear from the universe, and it's going to turn into energy. So subtract the two and get your delta mass. Convert that from AMU into kilograms. And then put that into energy equals change in mass times the speed of light squared. Now the answer you get is going to seem like a really small amount of energy. And it is. But realize that's the energy of a single nucleus. One atom of plutonium-238. So that is not the energy that we're getting in total. It's the energy we're getting per reaction. Okay, so now's where it becomes a little tricky. We start with 4.8 grams. In 90 years, give or take a few months, we're going to use half of that. So we're going to use about 2.4 kilograms worth of plutonium. So start out with 2.4 kilograms of plutonium. You're better off working it in grams because this is more of a chemistry thing, where grams is more of a standard. Okay, then what you want to do is realize that 238 grams of plutonium would be 1 mole of plutonium. Okay, just like you would have done back in your chemistry class. You then hopefully will realize and remember from chemistry that 1 mole of anything is 6.02 e to the 23rd atoms of that substance. That's Avogadro's number. It's the definition of a mole. And then finally, take those atoms, and 1 atom of plutonium will have whatever you found here, joules of energy. So working this all out, you will get the number of joules that will be produced over the 90-year lifespan of this plutonium. And realize it's not really a 90-year lifespan because it still has half of its energy left after those 90 years. But figure out how many joules we get in 90 years. Once you get the number of joules, I then want you to divide by the number of seconds in 90 years. That will give you the joules per second that we're able to get from this radioactive sample. In other words, how many watts? Now, make sure you remember that that's not going to be a constant, that we're going to get a lot of watts early on, and the watts will diminish as time goes on, just like the half-life graph shows us. Okay? But this would be the average watts we would get during that 90-year time period. And it's pretty amazing. This power source goes 90 years, giving us constant energy without us having to worry about sunlight, dust storms, clouds, winters, shadow, or anything else. It's an amazing source of energy. And that's where we'd like to stop for today.